Hello everyone, welcome to Course Seeded. So today's video is going to be a bit special because we'll be checking the algorithms which are used in networking. So first we'll be going with the directed graphs, then we'll be checking all the algorithms. So in last lecture I told you that you have to solve this question. How many cycles are present in the graph? But before giving the solution for this, I'll be uh, teaching you about the directed graphs first, and then we'll be going to that question. So what are directed graphs? So directed graphs are basically, you already know that they are graphs from, you can't travel on both nodes from each place. So basically what I want to say is, for if the graph is directed from 1 to 2, then you can only travel from 1 to 2. You can't travel from 2 to 1 directly. So that's the problem we have. So basically these are used in maps, in your Google map or other maps, whichever you use. So for the starter, we have like a cycle in this. So basically what is a cycle? If you can reach a node from uh, that node again, basically if you start from 1 and then you are able to come back to 1, then that means it was a cycle. So in directed graphs, it's hard to know whether the cycle exists or not, but in undirected graphs it's very easy. Basically you just have to check whether you reached 1 again or not. Basically in both cases you just check whether you can reach the same node again or not. But the only problem in directed graphs is you can have multiple ways in a single this. So if you go from 1 to 3, you might not be able to go to 2. So you'll have to check 1 to 3 and 1 this path only. If you try to check this path, then you might get lost. So we already know for undirected graph we just use DFS in a single line. But for directed graphs, you have to use like other methods. Well, basically DFS only you'll be using, but like a bit logically, you can say. So first we have from 1 to 1 you can reach in directed graphs or not. So first we'll be checking whether cycle exists in directed graphs or not. So what we can do is we can just create a function whether there exists a cycle or not, or the thing which we are traveling is a cycle or not. So at first we'll be having a node which we have to reach, and there will also be a like visited node. So we'll be storing that in visited array, and then we have, or you can just use vector over here. Well, next we have, next what we can do is we can just take a stack, result stack. So what you can do is you can store the result in this stack. So if something has not been visited, if node hasn't been visited, then you mark this as true, because now it's been visited, now it's being visited. And you also mark it in the stack, in the resulting stack, you mark this node as true, that we have traveled on this right now. So next what you can do is, well, basically we'll be backtracking to for this result stack. So whenever we'll be leaving this, we'll just mark that as false. So we'll be using backtracking in a few minutes or in a few moments. So next what we can do is, you already know that for DFS we just have to call for each neighbor, and then you can just go with your graph and then call for the node in that. Well, basically this is all the past work. You can just go and check what we do and what we have done in the past if you are unable to get what we are doing right now. So next what you have is if not visited neighbor, then what you can do is you can return true, or wait, and you can also do, and what you can do more is you can check whether the cycle exists for other neighbors or not. So you check for cycle and you check whether it has been visited or not. So if it's not been visited, then only you return true. So that's what we are doing. Otherwise, what you can do is, suppose if it has been visited, and also if the resulting stack neighbor, basically if this was also true and this was also true, then you can return true. Well, basically you have reached where you wanted to reach. Well, basically you have taken a whole this and then you have reached there where you were. So suppose if you were at 1 and then you reached 2, then you reached 3, then you reached 4. 1, 2, 3, 4. Then you went to 5. And suppose from 5, instead of going to 1, you went to 2. Then what this will do is basically this will just create an instance where so we have to, like, we haven't done that yet. So what we need to do is basically we have to create an instance where 1 is getting excluded, 1 gets excluded, and this whole thing stays. So what we can do is we can backtrack what we did. So basically we have already learned about backtracking. So we can just resulting stack node, we can just mark this as false. So if you don't know how to use or what is backtracking used for, then you can go to the past videos and then you can check them over there. So, well, basically let me just explain what we are doing. So in backtracking, what we are doing is basically we are removing the vertex from recursion stack before returning anything. So basically that's what we are doing. Then what you can do is we can return false if none was found. So this will be at the end even after backtracking. So this is what we have to do for this cycle exists or not in a directed graph. Let me first implement that and then you can check what I mean by that. Well, if you want to know even better how to apply recursion and backtracking, then you can obviously write that down in the comments that you need few questions to understand them. But if you already know how to use recursion, backtracking, and all the other stuff, then you don't need to comment, obviously. So let's create okay, so yes, now I can say. So at first let's create a function bool is cycle, and what we can do is we can pass the node and a vector which was visited, and we can pass a resulting graph, or you can say resulting stack, not graph, it's always the resulting stack. And what we can do is we can pass them by reference. And then what we can do is if not visited, so basically in the vector we are checking whether it has been visited or not. So okay, so instead of integer, let's keep it boolean data type. So if it's not been visited, then we can like visit the node, and then what we can do is we can just mark that as true. That means we have visited this node now, and we can just call for result stack. Next, what we can do is we can go to all the neighbors. We can call all the neighbors connected to that node. So we are calling all the neighbors right now. Okay, so we didn't take graph over here. Let me first take the graph also. Next we can do is for auto neighbors histograph. Then what we can do, we can basically check if neighbor was visited or not. So if neighbor has not been visited, then we can call the cycle function. So is cycle, and instead of like passing the node, we'll be passing the neighbor over here. And then what you can do is okay, so here I wrote neighbors, and over here I have to like, so for auto neighbor to graph node, well basically for that node we are checking all the neighbors connected to that. So if is cycle neighbor, then what we can do is we can check the visited array, we can pass resulting stack, and then we can do graph also. Yeah, so basically this is the correct thing we need to do. And then what we can do is we can return true if this holds correct or not. Next, in else if, we actually don't need to check whether it has been visited or not, because since we are writing over here not visited neighbor, that means if it wasn't visited, then it will automatically like capture this one. Otherwise, if it has been visited, then it will capture this one. So whether I write this, so whether I write this or I remove this part, that doesn't matter, because you know, like it already is there whether you want that or not. Next, what we can do is we can basically check for we can just go with the backtracking. So we'll be marking the node as false if nothing was found, and then we can just return false over here. So this should give us whether the cycle exists or not in that directed graph. So how do you take the input of directed graph? So basically, instead of like writing graph u dot pushback v, we'll be just writing instead of writing both of them, we'll be only writing the first one. Well, this will get commented out in our directed graphs. Well, why? Because that will be given to you that only from u to v you can travel, not from v to u, if it hasn't been given explicitly. So for now, let's write that one too. Okay, so now we have written what we needed. So we'll be just calling this function is cycle. So let me just call this f is sorry. So first let me take a boolean data type, whether it has cycle or not. and mark it as false. And then in the for loop, well, basically I'm using this for loop because there is a possibility that there are connected components present in the graph. So what you can do is whether we can check whether that exists or not. So suppose if there is something like this, and then there also exists this 4 5 6. So like these two graphs are components of a single graph. So basically we'll have to just check whether the graph has some strongly connected components or weakly connected components or not. So what you can do is for for all the nodes, basically let me write it node equals 1. So basically if you go in the last lecture, you can just copy that. You can basically just check what I'm trying to say. Then we can check if is cycle, and then we'll pass the node. So which node will we be passing? So we'll be passing the node itself, and then what you can do, you can pass the visited array, then resulting stack, and then we also have to pass the graph. Okay, so we didn't define anything yet. Let's first define them. So vector boolean data type, and then we have visited array n+1, and then we have one more boolean array. Yeah, so next we have just vector end. Yeah, so basically this is it. So if it has cycle, we can just say has cycle equals true. And just see out if has cycle, then we can just see out cyclic else. Okay, so this is what we need. Let's first write a graph. Let's write everything for this. So basically there are 6 nodes, 5 edges, and we have from 1 to 2, 1 to 3, 4 to 5, 5 to 6, 6 to 4. You can't write 4 6 over here. That will create some problem, as you already know. This is a directed graph, so we have to be careful what we write. 6 5, then we have 1 2, 1 3 4 5, and then 6 4, and then 5 6. So basically there are 5 edges and 6 nodes. Let's see whether we are getting everything correct or not. So there was some typo. Let's see if there are other typos also. 29th line. So so over here I wrote int instead of bool. So now everything should be good. Yeah, so everything looks good to me. So this was cyclic, yes, as we had this 4 5 and 6 4. Suppose if I change this to 6, instead of 6 4, I change this to 4 6. Basically 4 6 means from here to here. This won't form any cycle, because if you go from here, you won't be able to go here. So basically this ends over here. So if you go from 4 to 5 to 6, it will end over here. You can't go from here to here. So this should be acyclic now, since I've changed this input. And if this was 6 4, then cyclic, and here it is acyclic. Let's check whether it gives acyclic or not. Yes, so we are getting acyclic as the answer. Okay, so there was typo in this. So now it should be acyclic. Okay, so let's move to the next topic. Since the topics are longer than usual topics, we need to move faster than our usual speed. So we have done one topic for now. Next, we need to go to the second topic. So let's count all the cycles, whether they, how many cycles are there. So let's move to the new one. Number of cycles. So basically for checking the number of cycles, what you can do is, first you'll have to make a strategy. Now suppose if there we want to track the record whether we are traveling in a cycle or not. Like how many cycles are there, you can basically find that out by checking all the cycles. So at first, let's see what we need. Well, I won't be just counting the number of cycles, but I will also be printing all the cycles. Print all the cycles in graph. So we are doing 2 questions at once in a single go. So for competitive programming, you can just use the basic one, which I'll be telling you right now. But if you want to be even more optimized, then you can use the one that I'll be telling you later. Number of cycles. Basically, actually, I forgot the name of that. So I believe it was something like Johnson's algorithm or something like that. Yeah, so we'll be checking for the Johnson algorithm. You don't need to remember the name, you just need to remember what I'll be teaching you. So print all the cycles in graph. So for number of cycles, we can just basically count how many cycles are there. Basically, each time we are traveling from 1 2 3, what we can do is we can basically check whether the cycle was present in this or it was present outside this. 4 5 6. So suppose there are 2 cycles. Okay, so now if you want to like do it like this and this, so yeah, so now there are multiple cycles. So basically there are 1 2 3 4 3 cycles over here. Yeah, only 3 cycles are there. Now suppose if I also join this, can someone tell me how many cycles are there? Let's first check them one by one. For the first cycle, we have 1 2 and 3. 1 2 3. Well, basically doing manually means like it will take lots of time. So we have introduced some algorithms for that. The second cycle, you have 1 4 5 3 and then 1. And then what you have is you also have yeah, so you also have 1 2 3 4, and then you have 5 then you have 3, then you have 1. Basically you have this. Well, basically what I want to say is you can go from 1, 2, 3, 4, 5, and then you can come back to 3, and from there you can also go back to 1. So basically this will create a lot of tension in our work. Well, basically you have to like check how many are there this way. So that will create a lot of problem if we do it manually. So we have introduced 2 algorithms for this. So first, everyone must be knowing that we can just use a simple DFS and coloring method. So either I can skip that or I can tell that first, and then we can move to the next one, which is our like the one which I told you. I believe it was Johnson's. Yeah, so it was Johnson's algorithm. Next we have like 4, 5, 6, and then back to 4. There must be there might be more cycles. Yeah, so there was. We also have 4, 5, 3, 4. 4, 5, 3, and then 4. We also have this as a cycle. And suppose if I add something like this will also be treated as a cycle. 1, 4 and 4, 1 will also be treated as a cycle. But for now, let's leave it. For now, we just have these many cycles. 1, 2, 3, 4, and 5. 5 cycles in total. Let me first quickly check whether there are any more or not. Yeah, so there are no more cycles. So we just have these cycles for now. So now let me explain you the code that we'll be writing. So first we'll be checking for the DFS. Well, basically this one, or you can just directly go to the Johnson's one. So let me directly explain the Johnson algorithm. Basically, so the mechanism, or you can say the algorithm, thinking of algorithm of Johnson's algorithm. So the thinking behind this was, first you have to check whether there are strongly connected components or not, and then in the strongly connected components, you can just Johnson's process use as strongly connected components by like discarding nodes that that cannot form any further cycles. Yes. So suppose if there are no further cycles that can be formed, then you can use Johnson's algorithm. You cannot like use just at that time. It's basically the thinking behind that. Like if you are ending at some point, then you can just stay over there and you can just chill with that. Now suppose if you have like blocked paths which are like you can say that some paths become blocked. Basically what I mean by that is suppose you have 1 to 2 and then 2 to 3, and suppose instead of going this side your arrow was this side, so this is a blocked path. You can't just go from here to here. So what you can do is you can basically uh, go back to the same go back to the path, and you can just explore this one. And if there was some way to go from here to here, suppose if this was like this, then we could just simply solve for this one too. Basically by the way, this algorithm is the one which we use in networking, so be careful when you're using this. So at first we have 1 3 and then 1 2 3. Next we have like the cycle which we need, basically the code which we need. So this was the thinking behind that. The strongly connected components are the key factor. So at first we can just take a vector, and then inside a vector we can just take set, because we can also take a vector, but that will create some problem. So we'll be taking a set. or you can take vector. What's the problem? Vector and integer, and then in the graph. Basically, why I was taking set is because you can't have like 1 to 2 and then 2 to 2. So basically, taking set was the like logical thing to do. But since we are not using that much logic either way, I'm just taking vector and vector of vector. Basically, in networking, you will have to use set because if someone gives you a path which was already named like this, and someone tries to give you the same name for another path, then you would like to cancel that out, and you would like to uh, remove this one from here and just insert this over here. So there is a different logic behind that. So you're getting what I'm trying to say, right? Next we have whether we can just write the graph or not. So first we'll also have a start node. Let's say start node is 1 for now. Let's keep it nothing for now. And then again we have like cycle count, which is 0 for now. And then we also have a path, vector and path. And next what all we need is basically we also need a block, whether the path is blocked or not. So next we have we'll also be taking and well, basically these are your this is your number of nodes and this is your number of edges in the graph. So this should be what we need. So we also need a visited array, and we'll need many more. So well, basically if you remember the Tarjan's strongly connected component algorithm, or you can say Tarjan's algorithm, then you should know that we are going to use multiple of them, multiple vectors in this. So I haven't yet taught you about Tarjan's algorithm, but over here I'll try to summarize what is needed. So we can just remove all this, and we have yes. So that should be good. So what all do we need? Let's take everything as a global variable so that it's easier for us. We can leave them as it is in nm. Or we can take everything over here only. We will just have to get SCC. Well, basically we are getting the strongly connected components. So I have get a strongly connected components. So how much time? Let's see. Okay, so we have passed 30 minutes. So we need more 10 to 20 minutes to write the code, and then we are good to leave. So let me just write the code very fast and then explain it to you. So next we can just push that in stack. Basically, we are using the stack method for DFS. So, well, you can also use the recursion if you want. So, like if you want the recursion method, then you can type that in the comments. So next we have like set for SCC, and then we also have we also so we need this later for now. You can also define this over here if you need, but since we are just going for, or we can just like remove this from here. Basically, if v is less than min node, which is our neighbor, you can say. So we are taking neighbor up until now, and for now we have changed this to min v, and our minimum node is the one which we need. So if v is less than minimum node, then we can continue. So what we are doing is basically by writing this, we are just restricting the search. We are basically just restricting the search to induced subgraph, you can say. So, or you can say this v will basically if the neighbor has some close distance as -1, then what we can do is you can just call for the function which you have like currently made. What you can do is v comma rest things won't change, v comma des comma low. So we should also change this or not. So for now we aren't changing anything. See, then we have so for now we are good with this. Then you can have like low u equals minimum of low u comma, or we can just check for the neighbor also. So otherwise what you can do, so if it's in the stack, what we can do is, well, we can basically check for the, we can check the same thing, but we'll also be including the disk one. So, well, basically don't get worried if you are unable to understand right now. I'll be explaining this just after I've completed the code. I mean, right after I've completed the code. So if low u is double equals low v, or you can just say disk u. Then what we can do is we can define a set. Then what we can do is we can just go with the while loop. And then we can just check for the stack stop function. So basically this is the one we are doing like the DFS thing. Basically this is the basic DFS which we use. And then we are just checking out whether it was there in the stack or not. And then if that was false, then you can do a cc.insert v, then if you Sweden, then you can break this. And now suppose if you have a cc dot size more than 1 or scc dot size all equal to 1, and then we have the graph. Okay, then we can just take the pointer of scc dot begin. Basically this is just the 0 thing. And next we have like count start scc dot begin. So I have like 1 2 3 4 closing brackets, 1 2 1 2 and 3 and 4. Yes, so this looks good. What you can do is we can just push the current scc and scc. So this should be the thing that we need. Next, what you can do is basically you can find the scc with the last node index greater than equal to min node. So for that also we have to write the code, and then we can go to the Johnson's unblock procedure and then Johnson's core circuit DFS search, then we are good to go. So basically let's go to that also. So first let me write the complete code, or no, if I write the complete code I might not be able to explain you. So actually the video is getting a bit longer, so let me first quickly write the code and then come back to you. Yes, so I've written the code now. Also there was some error in my explanation. So basically this won't be a cycle because you know for something to be a cycle you have to like be able to reach every node from every node. So basically if you are at 2 you should be able to reach 2 also. So basically this won't be a cycle. So there are only 4 cycles, 1 2 3 and 4, 1 2 3 1 4 3 5 and all.